concerns are being raised tonight about a controversial chemical that has been found in canned food products.
Well, they certainly did, and some students over at A&M Corpus Christi used canned food today to create works of art.
Once limited to containers sealed by hand using solder in a slow process that kept costs high and volumes low, canned food by the 1910s had become a mass-produced staple reaching millions of households through a manufacturing process that bore almost no resemblance to the methods of the previous century. The machinery that replaced those methods was faster, more consistent, and capable of processing volumes that earlier canneries could not have approached, though the raw material entering every one of those machines still had to be grown, picked, sorted, and prepared largely by human hands before any of the equipment could begin its work. This video will take you inside canned food manufacturing in the 1910s to uncover exactly how fresh produce and meat were transformed into shelf-stable products capable of lasting months without refrigeration, why every stage had to be carefully controlled to keep food from spoiling, and how the canning industry's expansion during this period permanently changed the way populations across the world were fed. Right now, let us explore this remarkable process together. The production cycle at a 1910s cannery began not with machinery, but with timing. Canneries were deliberately built in close proximity to the farm supplying them, because the interval between harvest and processing directly affected the quality of the finished product. Vegetables and fruits began losing freshness, texture, and some nutritional quality soon after harvest, and fish and meat deteriorated even more rapidly. Horse-drawn wagons and increasingly early motor trucks delivered fresh loads to the cannery receiving area on the same day as harvest wherever possible. Upon arrival, each delivery was weighed and inspected before being moved to the sorting tables. Women made up much of the sorting workforce because canneries commonly employed them for grading and packing operations. Workers examined produce piece by piece, removing damaged, diseased, or undersized items that would affect the quality of the finished pack. Sorting standards varied by product and by the grade of pack being produced, but the principle was consistent across all canneries. Material that could not meet the minimum standard was removed at the earliest possible stage, before any processing labor had been invested in it. From the sorting tables, accepted produce moved directly to the washing area. Sorted produce entered the washing stage, where accumulated field dirt and surface contamination were reduced before heat processing began. Smaller canneries used stationary washing tanks through which produce was moved manually. Larger operations used rotary drum washers, cylindrical screens that tumbled produce through continuous flows of clean water, scrubbing surfaces through mechanical action while allowing dirt and debris to pass through the screen openings and drain away. Following washing, produce entered the preparation area, where peeling, trimming, and cutting reduced it to the specific form required for each product. Peeling was performed manually for most products, with workers using hand knives and mechanical peelers depending on the volume and vegetable being processed. Mechanical potato peelers using abrasive rotating drums were in use at larger facilities by the 1910s, processing significantly higher volumes than manual peeling could achieve. Uniformity in cut size was not simply an aesthetic consideration. Pieces of consistent dimension cooked evenly during retort processing, preventing some pieces from being overcooked, while others remained underprocessed within the same can. From the preparation area, cut produce moved to the blanching equipment. Prepared produce was blanched before filling, briefly exposed to boiling water or live steam for a controlled period that varied by product type. Leafy vegetables and tender items, such as peas, required only 1 to 2 minutes of blanching to achieve the desired effect, while denser products such as corn, beets, and carrots required between 3 and 5 minutes to ensure adequate enzyme inactivation and gas expulsion throughout the piece. Blanching served several functions simultaneously. It inactivated naturally occurring enzymes in fresh vegetables, including peroxidase and catalase, that would otherwise continue breaking down color, flavor, and texture compounds during storage, progressively reducing product quality even within a sealed and sterilized can. It softened tissue, making filling easier and allowing more product to be packed into each container without forcing. It expelled gases trapped within cellular structures, helping the food heat more evenly during sterilization and improving the vacuum achieved in the finished can after cooling. Blanching times were product-specific and closely managed, as over-blanching degraded color and texture before the can was even sealed. Workers transferred blanched produce to the filling area immediately after the blanching step was complete, maintaining the temperature of the product and minimizing the interval between blanching and sealing. A timing discipline that directly affected the quality and consistency of the finished pack. By the 1910s, the sanitary can, featuring a double-seamed lid applied by machine, had become the dominant format across the American canning industry, greatly reducing the need for solder and food contact seams while making sealing faster and more reliable. By the 1910s, the sanitary can, featuring a double-seamed lid applied by machine, had become the dominant format across the American canning industry, greatly reducing the need for solder and food contact seams while making sealing faster and more reliable. Filling was performed either manually or by machine, depending on the product and facility size. Liquid products and uniform small items, such as peas, were well suited to mechanical filling equipment. Larger or irregularly shaped items, whole tomatoes, fish fillets, meat portions, were packed by hand to achieve consistent fill weight and appearance. Following the solid fill, covering liquid was added, water, brine, tomato juice, or syrup depending on the product, to a specified headspace level that allowed for thermal expansion during retort processing. The headspace dimension was not arbitrary. Too little risked deformation during retorting, while too much reduced the vacuum achieved after cooling and affected seal stability. Filled but unsealed cans then passed through an exhausting step before the lid was applied. Open cans moved through a steam exhaust tunnel that raised the temperature of the product and displaced oxygen from the headspace. As the can cooled after sealing, the condensing steam created a partial vacuum that drew the lid firmly against the can body, providing both the characteristic concave lid appearance and an important indicator of seal integrity that inspectors used throughout the production process. Following exhaustion, lids were applied and double-seamed by machine. The double seam was formed by two sequential rolling operations that interfolded the edge of the lid with the flange of the can body in a tight mechanical joint requiring no solder or adhesive. A properly formed double seam provided a hermetic seal capable of withstanding the internal pressure generated during retort processing without leaking. Factories periodically checked seam quality using inspection methods to ensure the seal met production standards. Sealed cans were loaded into retorts, large pressure vessels manufactured from heavy steel plate, capable of holding several hundred cans per batch in wire baskets stacked inside the vessel. Once loaded and sealed, the retort was pressurized with steam to temperatures above the normal boiling point of water, with exact temperatures depending on the product being processed, and held for a processing time determined by the specific product, can size, and the temperature required to destroy dangerous microorganisms, including the spores responsible for botulism. Processing times varied significantly by product. High-acid products such as tomatoes and fruits required less severe heat treatment. Temperatures at or near 100 degrees Celsius for relatively short periods were sufficient to render them shelf-stable. Low-acid products, including most vegetables, fish, and meat, required higher temperatures achievable only under pressure, held for periods ranging from 20 minutes to more than an hour, depending on can size and product density. During this period, researchers including William Bigelow and Charles Esty at the National Canners Association were beginning to develop the mathematical framework for calculating minimum safe processing times by product and can size, work that would eventually standardize retort schedules across the industry and dramatically reduce the incidence of spoilage from underprocessed commercial canned goods. Following retort processing, cans were cooled rapidly under cold water sprays or in cooling tanks to arrest cooking and prevent texture degradation from residual heat. Cooled cans underwent inspection before labeling. Workers examined each can for seal integrity, seam defects, swelling, an indicator of microbial activity inside, and physical damage from handling or retort loading. Any can showing signs of a compromised seal or abnormal internal pressure was removed from the production lot immediately. Only cans passing the full inspection standard advanced to the labeling line. Paper labels were applied to the exterior of each inspected can, either by hand at smaller operations or by early mechanical labeling equipment at larger facilities. Labels carried the packer's brand name, a description of the contents, the net weight, and in some cases the geographic origin of the raw material, information that was becoming increasingly important as national brand competition intensified across the canned goods market during the 1910s. Once labeled, cans were packed into wooden shipping cases and stacked on loading docks for transfer to railroad freight cars and coastal steamships serving regional and national distribution networks. By 1917, the demands of the First World War had accelerated canning industry output dramatically, with American canneries supplying hundreds of millions of cans of meat, vegetables, and fish annually to military procurement agencies, supplying Allied armies and military depots. The combination of reliable double-seam sealing, pressurized steam sterilization, and expanding rail distribution had transformed canned food from a supplementary convenience into a logistical foundation of industrial-scale food supply, built on a process that began, every single time, with someone sorting through a pile of freshly picked vegetables by hand. Whether those workers found comfort in knowing their careful sorting would eventually feed soldiers thousands of miles away is something the production records, characteristically, did not record.